Hello everybody, welcome to this workshop session on thermal simulations. My name is Sam. I'm going to talk more about myself in a short time. Before that, I would like to confirm if the GoToWebinar application works perfectly for everybody. So if you're able to hear me, please click the raise your hand button in the GoToWebinar application. I'm just looking for some more hands. Okay, I can see a lot of them. In the meantime, if you're not able to hear me during the course of this webinar, you can at any time call to the toll-free number which has been already sent to you. Or you can check your audio settings and then it should be fine. Now, yes, you can put your hands down. Thank you. So this workshop session is divided into three different sessions. So taking place in like a week interval. So the first one is right now happening, and it's basically on the heat transfer basics and the simulations explaining this one. And the second one would be on next Tuesday, which would be a dedicated session for conduction and showing its application and examples as well. And the third one would be a focus on convection. And for your information, we record this session, so it is also uploaded to YouTube and published to our forum later. So you can check our forum latest by tomorrow, and you will also receive an email notification regarding the same. Now, I have planned a schedule for the next 1 hour, which is going to be like a brief introduction about the three phenomenon happening, thermal phenomenon, and then let's jump into the session. About myself, my name is Sam Prabhu Jesu Rajendran, as you can see it from here, and I know it's quite big, so you can refer me as Sam in any of the email or forum correspondences. So I basically have a mechanical engineering background, and I specialize in CAE, which is computer aided engineering, essentially in CFD, computational fluid dynamics, structural mechanics, and multi-body simulations as well. So I have quite some experience working with multi-phase flow simulations, phase change modeling, and many other fluid flow simulations with regard to CFD. And in structural mechanics field, I worked with material modeling. And at SimScale, I do a variety of works, primarily support and service. So if you had submitted some support queries to SimScale through any channel, then you probably expect a reply from me. And this is going to be the agenda for this first session. So to start with, what is SimScale all about? So to start with, why should you actually simulate something? And then why should you use SimScale to simulate it? And then what are the features offered by SimScale, say the fluid simulations, structural mechanics, and the other features? And then in a nutshell, we explain about the three heat transfer phenomenon. So basically the conduction, convection, and radiation with some simple examples to illustrate the basic physics. And then about the thermal simulation types. So we actually have the fluid analysis and the structural analysis. So, but the basic approach is different for both the cases. So we try to differentiate them starting from meshing and discretization. And then we would go about how to do a simulation in SimScale. So we generally call it a three-step process, which you will later see, and then look into a few thermal simulation setups. And then I would be showing you a live demonstration to a simple setup where you have examples of all the three heat transfer changes and as also a real world case. And then get some interesting results out of them. So we analyze those results, make comparison, essentially get some colorful pictures to interpret, and then make some comparison plots. And finally, we have a Q&A session So if you have any questions as the session progresses, you can just type them in the question box in your GoToWebinar app. So I'll try to cover them up at the end as depends on the time. As the number of attendees is very high, so I might not be able to answer all your queries. I'm sorry. But I'll try to cover most of them, and essentially the most common and most important ones in which like many people have a doubt with. If it's not possible for me to answer all the queries or your particular query during the session, then probably you can put your queries in a forum. So it is a place for all your questions, and probably the experts and the power users in our forum can answer your questions. So to go to your forum, probably you can look into the screen where it is simscale.com/forum, and you can go here and you have a dedicated page for this. So it says a discussion page for this analysis. So you can just post your queries and we'll try to answer them at the earliest possible. And a quick note, I believe it would be a better option for all of you to put your queries on the forum than just sending support tickets. It's because of the reason that like most people have the common doubts. So it would save time for all of us in that like people could actually refer to forum. So if they have the same doubt, they can get it clarified essentially. And now a short note on who we are. So SimScale is an online simulation platform, so completely based on cloud. All your model setup for numerical computation is solved based on our cloud computing capabilities. So to start with, why do you actually have to do a simulation? So every design process essentially has so many steps in a traditional way. So starting with and this is a step-by-step approach, starting with design stage, and then you do a prototype, then you test the prototype and do changes again, and again build a physical prototype, test it, changes. And so this is a cyclic process, and creating a part physically involves a lot of human as well as machine work. So it consumes a lot of time and money. In order to save those, all of these simulation comes into play. We make design processes much easier using simulations. So you now know the importance of using simulation, but why should you use SimScale for this? So there are three important things which I would say that SimScale is a good choice for you to simulate. The first one being the accessibility, and the second one is the cost efficiency, and the last one is availability for everyone. So accessibility, you don't need a high performance a RAM, a graphics card, or any other hardware for that matter, or even a big software installation in order to perform a simulation. So basically the commercial softwares requires either a hardware or software installation, but you don't have any of these required for SimScale. You should just have a PC, a laptop with a browser installed in it, and then you're good to go. So you can perform high performance computing on our cloud-based platform. All you need is an interesting idea, of course, and a CAD model with a basic knowledge of how to set up a simulation. And essentially we could help you with getting that through. As in, once you have an interesting idea, probably you can post it in the forum as well, and then we can help you set up the simulation to get some interesting results. And the second one being cost efficient. So SimScale usage is basically for free. So anyone can just sign up to SimScale and you can just start simulating for free. We have a concept of public and private projects. So the public projects are accessible to everybody. So if you are a free user and then you just sign up, you get access to all the free projects which are public. And if your project is going to be private, it's only you who are going to see it and no one else can get access to the project. So in that way, if you can use everything for free. And if you wish to have private project, then you would have to pay something. And in here, you pay for what you actually use. So you are being charged based on the core hours, so which is scalable and on demand. So you only pay when you have a demand. So that's the advantage of using SimScale. And I believe comparing to many other softwares, this is much cheaper to use. And for everybody, this is a crowdsourced library, so based on public projects from many community users. So if you could actually look into the public projects, so again, when you go to simscale.com and search for public projects, you have close to 15,000 projects to search from. So if you just have an idea, you can just bump in and see and do a quick search if anything matches your idea. Say for example, I want to simulate a windmill, and then you just do a quick search and you get all the simulations, all the projects which are in wind turbine, and then you can simulate them. So this is one really good advantage of having public projects. Oh, I'm sorry, there's some issue with, let me get back to it. So you have many public project templates which you can just copy it and then start implementing your own values to it and then start simulating. So you get the public project list. So yeah, we have wind turbine. We have a lot of them. So you get a very good idea of how to go about simulating this. And now the types of simulations, we have fluid flow simulation. So basically we have the different types in them, incompressible, compressible, say multi-phase simulations, scalar species, and the one which our focus today is on the convective heat transfer, which is the buoyancy driven flow. And in this case, we only have the fluid domain and try to simulate something on this fluid. The second one would be the conjugate heat transfer, which has a solid as well as fluid domains present. So in principle, you can simulate the interaction between the solid and the fluid domains. So this is an advantage of using the conjugate heat transfer simulation. And there are many other advanced applications, see rotary missions, porous media. In general, any of these fluid analysis type can be coupled with the advanced application. So in principle, you can use incompressible flow types with rotating machinery, porous media, and so on, say multi-phase with a 6 degree of freedom motion in a case of a boat floating. So you have air and water to a multi-phase simulation, and then you give a 6 degree of freedom for the boat. So it's easy to simulate, and all our CFD simulations are based on OpenFOAM and SU2 codes. Both of these are open source softwares, open source codes available, and then we use them to simulate the fluid flow analysis. And in structural mechanics field, we have again various analysis types, static, dynamic, frequency, modal, and so on. But our interest today would be the thermomechanics, which has heat transfer and uncoupled thermomechanical simulations. So in heat transfer simulations, the temperature changes in the solid due to any heat transfer changes, but in uncoupled, it also includes stresses due to any pressure loads and so on. So it includes both due to heat transfer as well as pressure loads, the stresses induced in the solid. So, and the structural mechanics solver supports all of these, contact mechanics, parts and assemblies, and so on, and we use Calculix and CodeEster as the solver. There are other type of capabilities as well using SimScale, say like discrete particles and acoustics, but these are not our concern for the day, so might be useful for you if you would like to know for simulating any other cases. Okay, now after having a short introduction about SimScale, now let's dive into the topic. So there are three basic heat transfer phenomenon. As I told you earlier, they are conduction, convection, and radiation. To start with conduction. So the term defined for heat transfer between substances which are in contact. So if there are two bodies in contact, then conduction comes into play. Or it can even be a single solid which has a different potential. Say one is at a higher temperature, the other one at a lower temperature. So heat conducts from the high end to the low end. This is predominant in solids, and then it is comparatively less seen in liquids, and it is seen least in the gases. Apparently it exists in all the phases, but it is least existent in gases. This takes place essentially because of vibration in particles. So you know that in solids the particles are tightly packed. So when there is vibration, so it gets transferred to the particle, to the next particle. But when you consider the case of gases, which are like loosely packed, even if you have a vibration, it doesn't affect the surrounding particles so easily. That is why like the conduction effect is comparatively less in gases than in solids. As a simple example, we could consider a pan on a hot plate or an induction stove. So we heat the induction stove and the pan is automatically heated. So this is an example of conduction. And from the formulations, you can see that the heat transfer value is directly proportional to the temperature difference between the hot and the cold end. So in the example case which I just told you, our induction stove would be the hot end and our pan would be the cold end. So you have the temperature difference between them, and this is directly, the difference in the temperature is directly proportional to how much the heat transfer would be between them. And this is an example of conduction using simulations. So basically you have the heat transfer in spark plug in automobile. So heat is transferred from one end to the other because one end is always heated when the vehicle is running. And then you have heat transfer in sink through LED. And this is just the test case which I'm going to show you today. So we are heating on the top and the bottom end is just kept at room temperature. So for different materials, how does heat transfer take place? So this is a simple example. And next we go to convection. Convection is one where the heat transfer is achieved by particle movement. It's a characteristic of fluids. So essentially it's liquids and gases. I would say a typical example of this is in winter season, you feel cold because of convection. So the air around you removes the heat from your body. So this is a simple example of convection, and this is done naturally. In principle, you can get the required heat transfer or temperature if you artificially or intentionally blow air over something. So I can just show an example. So in this case, it's a data center. Obviously, this is a much reduced model, so a real data center would be much complicated. We just show you how a convection simulation works in a data center. So when air flows over here and you try to blow air into the domain with a particular velocity, and then you have heat in these surfaces. So these are the heated surfaces because of the server vents being heated. So the air which comes in, cold air which comes in, actually takes away the heat from the surfaces and goes via the outlet. So you can control the amount of heat being taken from the surface using the velocity. So this is, as I told you, it's a case of force convection, which can be used to for various heat transfer applications. And even in this case, the heat transfer is directly proportional to difference in the temperature. So here it is the temperature difference between the surface and the ambient. So the surface temperature and minus the ambient temperature is proportional to how much heat transfer would take place. Another typical example would be a room heating during winter. So you turn on the heater and the hot air tends to move up, and this is one other example of convection in a room. And the last one, it is radiation. So in radiation, this is the third heat transfer phenomenon, and the energy transfers through waves. It does not require a medium or any contact for heat transfer to take place. It can even travel through empty space. It can travel through empty space, which is called uh, infrared radiation. And this phenomenon is by thermal radiation. And this is predominant at higher temperatures. So only after some particular temperature, we couldn't say it specifically, but only at higher temperatures the radiation becomes predominant. This is evident from the formulation of radiation. In the previous two cases, the heat transfer was directly proportional to the temperature difference. But in case of radiation, the radiated power is proportional to the difference between fourth power of temperature. So which is, you have say something like this. This is a simple case of radiation. So I would explain this later because this is as well our trial case. I would explain the significance of the results later, but you know that this is a hot surface and this is the ambient. So the temperature at the hot surface to the power 4 minus the temperature of the ambient to the power 4. So that makes a huge difference since it is to the power 4. So when the difference between the surface and the ambient is high, the difference is going to be very high. So that is why this is most evident at higher temperatures. And there are various examples of it. So when you have a highly heated plate, radiation takes place in it. Now, the general thermal simulation types. So we assume a simple case, say a flow-through pipe or a rectangular cantilever beam. So one for a fluid simulation and one for a structural simulation case. So if we know the dimensions of all of them, so it is possible to find an analytical solutions using the partial differential equation. But what if, so we have the simple geometry, we use the simple formulae and then try to derive the results. What is the bending moment, how the flow would be, and so on. But what if the complex becomes we have a complex geometry? In this case, it would be hard to use our usual formulation. So we discretize the domain into small geometrical shapes and then try to apply these governing equations for each of the subdomain. This process is called as meshing or discretization. So we are dealing with thermal simulations, which are structural as well as fluid, and we use two different approaches for this. One is called the finite element approach and one is called finite volume approach. Now we would have a short discussion about what each of them are. So first, to go with the finite volume approach. In the finite volume approach, the domain is divided into small control volumes where the variable of interest is located in the center of volumes, which means, so if you look at the image on the right, it is divided, our whole geometry is divided into number of small cells. So in this case, whatever value is being calculated, say the flow value of velocity, pressure, or whatever it is being stored at the center of each cell, so the centroid of each cell. And this principle is usually applied in CFD applications. And interpolation between different cells take at the centroid of the cell. So this interpolation is required to find the solution for the entire flow domain. And as I told you, it is used in CFD applications. So in convection problems or CHD problems, we use this finite volume approach. And the next one is finite element approach. So in this case, again, the domain is divided into smaller volumes, but in this case, the variable of interest is located in nodes of the volume. So nodes are the corner points of each of the cell. So this is a tetrahedral mesh. So for every small cell, there are 4 corners. So all values such as stress, displacement, everything is being stored at all corners of the cells, and these are used for interpolation between the nodes, and they are most commonly used in structural mechanics applications. So like these are two structural mechanics applications where this is a thermal analysis on a PCB, so heat transfer analysis, and this is a thermal shock analysis, which also this is kind of a thermostructural analysis where I told you you also take the load into consideration and find the effective stress because of the load applied and as well as the temperature differences in it. So now using SimScale platform to simulate, as it says, there are it's a three-step process, which are you upload the CAD model and then you mesh and simulate it, and finally you post-process the results. Look, from the basic overview, it looks simple though, but let's see how this works. So we have 4 case studies. The first 3 are just for this study purpose, and the fourth one is a real world case. The first one is with just conduction. The second case is with convection as well as radiation to show the difference between convection and radiation. And the third one has its spotlight on a heating. A spotlight, it's a lamp, so it is being heated, and what if it has only convection, and what if it has conduction as well as radiation? So how does it work? And the real world case is a CFL, the bulb, and in this case we only take convection into consideration and probably conduction between these two. So we quickly go through a live demo on the platform. So for the first case is just a conduction, which is a transient heat transfer analysis, which I'll be telling you now what a transient analysis means. And we apply temperature and no convection and radiation at all. So it's just conduction going to be here. And we simulate it for a total of 5-minute physical time. And this output which we expect out of it is the temperature distribution in the domain and the heat conduction in different materials. So to start with, so this is when you log in for the first time. Oh, I believe I should show you this. So when for the free users, sorry people who have attended the workshop or webinar or even worked on our platform earlier, this might be kind of repetitive, but this should be helpful for the new users to set up, have a quick start to our platform. So you just have to create our account, fill it up, a 2-minute process, and then you're good to go. And then press login to start, and then you end up in the dashboard. So now click on new projects. In the dashboard you see all your projects. You also see the forum activities and the latest jobs which you did. You create a new project with the title whichever you want and a description if required, so that the people who refer your project can have an overview as to what you have done. And category, you can either upload the geometry here, or maybe after you create the project and you can upload the geometry later on. Now this is what I told during the beginning of the session, having a public or private project. So you can have a private project only if you are a customer of SimScale. You can just use a public project. You can create a public project. In this case, I already have my projects, so I'm just going into them. So once you click it, you have the project open. So you have the project overview window, and then just click to open it. Okay, so now I'm going to show you the example of conduction, which is multiple slabs. So here we have 4 slabs. We have 4 because we want to assume different materials for each slab and analyze how conduction takes place. So this model was done using a CAD software, and you can either import the model in any of these 4 formats into the platform, or you can also use the import from Onshape. Onshape is an online CAD software, just like SimScale is for simulations. So you can log in here, create a geometry, and then directly import it from Onshape. So to start with a mesh, create on this one the geometry which you want to mesh and click on new mesh. So right now we have only 3 meshes here which are already actually created. So I just want to show a demo of how this is being done. So once you click on that, you have a 4th one created, and you can select any of these mesh types, and you can go through a documentation as to how you can choose among these. So for this particular case, we use a tetrahedral parametric mesh. So after meshing, it looks like this. So we discretize into small domains. In this case, we use something called a parametric mesh, which is kind of a manual mesh. We try to define the edge lengths here so that we control how many cells we want or the length of the edge which is required. And then you just mention the values and click on start to start the operation. And this would not take long, probably less than 5 minutes to generate this mesh. So once this mesh is generated, now you can go to the simulation designer. So in SimScale, there is one thing which you have to remember. As simple as that, it's always either left to right or top to bottom. So on the top tabs, you go from mesh creator. So once you're done with the mesh creator, go to simulation designer. Once you're done with the simulation designer, then to post processor. And here on top to bottom, so from geometry to mesh, and even in mesh, you go one by one. So here you don't have many options, but when we switch to the simulation designer tab, you have many options, and you can see that you can just go from top to bottom, step by step, in order to set up the simulation, and it's quite easy for you to understand. Now, going into the simulation designer tab. So this is our case for conduction. In order to actually create a new simulation, click on new simulation and then choose the required analysis type. In this case, we will be doing a thermostructural analysis, so you can use either one of these. And for this particular heat conduction application, I'm going to use Heat Transfer Advanced. And Heat Transfer Advanced allows us to use a manual time stepping, something called a manual time stepping, which I'll tell you at the end of simulation setup. So that's the main reason why we use this advanced solver. But for the rest of the simulation, we'll use the regular heat transfer analysis type. This is because an auto time stepping would be sufficient. So once you press this and then click save button, and then as discussed in the problem statement, it is going to be a transient heat transfer analysis. So what is a transient heat transfer analysis? If you want a time dependent solution, then you go for transient analysis. A steady state analysis gives you the final solution at, say, infinite time. So after all the heat transfer takes place, what is the final temperature distribution in the domain? That you can see from the steady state solver. But as time progresses, if you would like to know how the temperature changes happen, then you go with transient simulation. So, and then once you click the save button, the simulation tree automatically is generated. So in this simulation tree, the red buttons are the ones which are mandatory fields, and the green ones are successfully assigned. If it's a blue one, it's optional field. You can either leave it empty and it doesn't matter, either way your simulation would run successfully. So we have already set up the simulation, so I'll show you a demo on this one. So as I told you earlier, it's heat transfer advanced and transient type. And then we go to domain. So domain, one advantage with SimScale is that I told you we'll be doing three types of analysis, but you can have all the three types in a single project. So you have the geometry of all the three and the mesh of all the three in a single project. And then you can even have the simulation of all the three under a single project. So you can have multiple multiple simulations, which are completely different types, completely different meshes. So for this corresponding simulation, you assign the mesh. So in this case, it is going to be the multiple solid plate mesh. And then it is up to us to define the topological entities. This is an important aspect if you would like to group your entities for assignment. Say you have 4-5 surfaces on which you collectively have to give a condition. Then you actually say click those surfaces and then select new from selection and you give it a name and it automatically appears here. So when you go for any assignments later on, you just have to select this and then give the condition, and all of these spaces are automatically being assigned with that condition. So that's the advantage of using a topological entity set. So, and contacts in this case is essential because we have 4 different solids. As you can see here, they are completely different solids, so we need to tell the solver that there is a connection between each of them. So we define something called a bonded contact. When you select them, you can see that you cannot see them right now because it is in this surface which is in between them. So what you can do is you can go to selection and click on isolate. So here you can see the master entities, and again you can see the slave entities. In this case it is going to be the same. You wouldn't see the difference, but in principle they belong to different solids. So previous time it was the master entity was from the face of this solid and the slave entity was a face of this solid. So now you can see the difference. And then you now set up the materials. So first you define a steel. You already have a material library from which you can import the material, a list of materials. So you can just select on the material, click save, and you automatically have it here, and then you assign it to any particular volume here. So in this case, steel is assigned to this volume, the first one, and you have acrylonitrile butadiene styrene. So this is a plastic material, and this is being assigned to the second solid. Copper is being assigned to the third one, and lead to the fourth one. Each one has its own material properties, and the most important properties for this, at least conduction, would be here. The kappa would be the thermal heat transfer, the thermal conductivity, which is kind of the important parameter for the conduction problem. So we define an initial temperature. So as I told you earlier, you always go from top to bottom. So it makes things much simple and easier. Top to bottom. So now going to temperature, you define a room temperature 20 degrees Celsius to the whole thing, just an assumption, and then you create boundary conditions. So here we say there is a temperature load on these phases, and the temperature load is given in terms of function. So how is this function defined? So you have this function here. In principle, the alphabets, characters shown in red are the conditions. So this is basically an if-else clause. So if the temperature is less than, if the time is less than 50, this formula is applied. This value is calculated. If it is greater than 50, this value is applied. So it calculates, and this calculation is based on the fact that until 50 seconds out of the total 5 minutes, we actually ramp the temperature, start the temperature from room temperature until 773 Kelvin, and after 50 seconds it is going to be constant at 773 Kelvin. That is the main idea. And then here we use the stepping list, and this is why we actually used the advanced solver. So here we actually force this time interval, and that's the reason for using advanced solver. And then you create a new simulation run. Once a run is created, you just select the run and click the start button, and it automatically starts running. Now we have to go for the next one, which is the post processor. So post processor, if you want to get the result for the corresponding simulation run, you can just click here and post processor results. You are directly redirected to the solution field of that particular simulation run. So you can see all the simulations here. You have the possibility to view the mesh as well, and to save screenshots or saved states. You can just save some states so that you can come back later again to view it. So here you can see the temperature distribution in the whole domain, and we would be discussing this later in the session. Right now I would be showing you the subsequent convection as well as radiation models now. So the second one would be convection and radiation. So this is going to be a steady state analysis which involves convection as well as radiation, and since this is a steady state analysis, it doesn't really matter how much time you simulate it for, because you only get the end result, so it is just for 1 second. And in this case you have this, it's just a rectangular plate, and to measure it we just use an automatic measure. An automatic measure, depending on the geometry, it automatically calculates the edge length. Previously we used to give a value, but in this case it just calculates a value automatically and then measures the domain. So now we go on to the simulation setup. The same thing as I told you why we use heat transfer. And here we don't have contacts because it's just one solid. We select the particular domain and then we assign steel material to it. The initial temperature is 30 degrees Celsius, which is 303 Kelvin. And now comes the load part. So we say that we apply a 1000 watt load to the complete volume. So the volume dissipates a load of 100 watts, and depending on the volume we give the value as this 20,000 watt per meter cube. So now we define a convection here, convection with a heat transfer coefficient. So the characteristic of a convection simulation is a heat transfer coefficient. This decides like how much heat transfer would take place. So this is one case. In the second convection we give a value of 50. So just to see the difference as to how a 5 and a 50 surface reacts. And on the other hand, we have radiation defined on the other two phases. So radiation with an emissivity of 0.9 and the other one with an emissivity of 0.1. So what is this thing called emissivity? So it's a characteristic of radiation. So if emissivity is equal to 1, it is called a black body, which can take up radiation completely or give out radiation completely. So it's like it completely dissipates the heat. And an emissivity of 0, it reflects everything. So it accepts nothing. It's like, for example, you can assume a shining surface. So that's an example of an emissivity 0 surface. And for emissivity being 1, a completely black surface or a rough surface is a good example. So we define this case and create a new simulation as the previous one and then run this again. So we would see the results of this as well at the end of the discussion. And now we go to the third one, which is the case with radiation, like how radiation affects. So this is also a transient heat transfer simulation run for a maximum time of 2 minutes. and a volume heat flux is applied to the body. So in this case, this is going to be the geometry. So it's a light bulb where we have something over here which is circular, but then it's computationally expensive to include that and simulate, and it is of no physical relevance. So in principle, we only simulate this. And again, we create an auto mesh over this. And going back to the simulation. So simulation, one case, we only define a convection over it. And the next case, we define a convection and radiation over this one. So we choose the heat transfer analysis type as to be transient. And now, since this is a light bulb, we define glass material to this one. Here comes the part. So we define a volume heat flux to this. And for transient simulations, people keep in mind that this is kind of sensitive. So if you like directly give the maximum value to it, there's a possibility that the solver could crash. So what we do is we ramp the value. So we run it for 2 minutes, but we say that the first 10 seconds, the heat rises slowly and then it's constant. So essentially in this region, it is going to be constant. But how do we do this? So we just create a table where you have the time and the volume heat flux, and then save this as a CSV file. So a comma separated value file, which can be uploaded here. So only CSV files can be uploaded here. You can look into the documentation for more details into uploading a CSV file. So we give this value where this value corresponds to a 51 watt power, and a convection is defined in all the surfaces except this one, because this is connected to the other shining surface over it. And now we simulate this case, and in the next case, the only difference is that everything is going to be the same essentially, but so we have the convection as well here, but we also have radiation defined in the same surface as convection. So we only have this difference, and we now try to find the different solutions. Before that, the real world case as well. So now we consider a CFL, and this is a steady state heat transfer analysis with a volume heat flux defined, and since it is steady state, we only simulate it for 1 second. So this is the original bulb, and most important thing, people keep in mind that simulations is kind of tricky. So it's always the best way is to break down things into simpler aspects, simpler parts. If you have a very complex model, big model with very difficult or multiple boundary conditions, etc. So, and you get an error in the simulation, you really don't know where the error has occurred. So what can be done is you can simplify into small steps, or try to use a reduced model and slowly increase the complexity step by step in order to get the final results. In this way, you can like actually know where you are committing a mistake or the error comes from, okay, this particular thing. So in this case, this is the model. This is a model from GrabCAD, one of the users in GrabCAD. So now we simplify it. In the threads, I believe they don't contribute so much to the heat transfer coefficient, so we try to neglect them, simplify it, and one other advantage is that we take the advantage of symmetry. So since it is going to be the same everywhere, we only take 1/4 of this model and simulate this. So I again do automatic tetrahedral meshing. It looks like this. And to set up the simulation, it is again heat transfer advanced solver. And in this case, since there are more than 2 materials, actually 3 materials, so we define contacts. So we assume this to be, the bottom to be an aluminum and this to be plastic. So this is one contact, and the second contact would be between the plastic and glass. So now heat transfer takes place between them as well. We define glass, the plastic, and the aluminum. So defining the boundary conditions, we give a temperature of 40 degrees to this one, and a conductive heat flux where you expect it to get heated. And the volume source is only the glass, which is 15 watts. Now we try to simulate this and get the results out of them. So now let's discuss all the results one by one. So this is the first case, and from this one you can see that, say, assume copper. So you can see that the temperature rises fast in case of copper. So the temperature increase can be felt at the bottom very soon in case of copper. Probably the next one would be lead, and the next one would be steel, and the least would be the plastic. But why is this? This is the properties of metals. So metals actually are good conductors. So conductivity is the thermal conductivity value is high for metals. And even in metals, they have differences in which copper is the highest value. So you can also see it from the graph that, say, at a value at a distance of 1.5. What is this 1.5? So from this top point, we take a distance of 1.1 meters. So somewhere over here. So at 1.1 meters, at some particular time, we see that copper already has reached from the top where it starts. It's around 773 Kelvin. And this point has already reached around, say, 5 or 620 Kelvin. At the same moment, lead is the next highest good conductor, which reaches around 493 Kelvin at the same instant. And steel is much lesser, and plastic doesn't even rise because plastic is really a poor conductor of heat. So this shows the conductivity, and here you can also see the conductivity between them. If there was no conductivity between them, you should see that the lead should have a flat rise just like you have it for copper. But then you see this profile because of the reason that you have heat transfer from copper to lead. So you see that the bonded contact works well. So the contact definitions actually work well in this case. So now moving on to the next case. The second case is where we defined convection in two phases and radiation in two phases. So you can see that when a lesser convection, so comparing these two, this is lesser convection phase, and comparing these two, this is lesser radiation phase. So at the juncture of these two phases, you have a high temperature over here, and this is due to the reason that the dissipation is very less because of low convection out of it and low radiation. Whereas if you could see on the other side, this has high convection and high radiation. So heat is being dissipated really fast, and you see the temperature reduces in this area of the domain. So this essentially shows how convection and radiation could work. The third one is for the spotlight. Yeah. And in this case, you can see, so this case is with only convection, and this is when we have convection and radiation. So when you see from the scale, say around, say, until 430 Kelvin or 450 Kelvin, yeah, again when it starts. So both are blue, it starts changing the color until a particular point. So after some point, you can see that this gets to red much faster than this one. The one with convection gets to red much faster. This is due to the reason that radiation, when after a particular point, actually leaves out, helps in heat transfer, because of which the temperature increases not that much compared to this one. Like the heat is being transferred through radiation to the ambient area. To see it from the plot, we consider a point on any corner of the cylinder. So you say, for example, at this corner. So as the time increases, say until 430 Kelvin, both temperature of the convection and the convection with radiation are almost the same. But after that, you see a vast difference. So at the end of 1 minute, you see that the case with radiation reaches probably around 750 Kelvin, but the one with only convection goes until 920 Kelvin, which is like far too high. So this is the effect of radiation. So you essentially have radiation everywhere, and radiation comes into play only after the higher temperature range. So this proves that. And a simple comparison as a previous one as well, we consider a line in the same spotlight from center to the corner, to one corner. So when we consider a line, the the temperature in the center should be really high than the one in the corner, and heat transfer should take place. So as you can see, for convection, the value is really high. So this is at the center, the value is high, but even as it reaches the corner, it is around 920 Kelvin as discussed in the previous graph. So at this point, it is 920 Kelvin. But when you see the case with radiation, as you go through the from the center to the corner point, you see the value is much lower and radiation has a better effect. And this result is seen after the entire 2-minute time span of the simulation. For the real world case, that is the heating of CFL, there's something called the TDP, which is thermal dissipation power. So for the CFL, it is say 15 watts as defined in the boundary conditions. And we just try to analyze the maximum temperature reached because of this. So how the temperature distribution takes place between the aluminum plastic or the plastic glass, and how the temperature varies in this case. So this could be a good study. So you can find the link to the projects. We would also put these links in the forum. As I told you earlier, you have this discussion page, so you feel free to like upload your questions. And if you have some interesting problem statements, you can just put them up, and then we'll definitely give you ideas on setting up the simulations as well. And so you can have this as an example to like understand how convection, conduction, radiation works. You can just take them up, make changes to the settings, and run some trial simulations. And that's it. Thank you for joining. And let me now check out for questions. Okay. There's one question from Bob Hertlin. If I cancel my subscription, are my private simulations and models deleted from the server? No, they are not. You continue to have them. You can just switch to public projects mode, and then you can continue working it. Which FES solver code are you offering? It's a question from Gurinder Singh. And we, as already discussed, we use Calculix and CodeEster. So Calculix is the heat transfer and the uncoupled thermostatic problems, and the advanced solvers are CodeEster based solver codes. Okay. And there's a question from Ahmad Riyadali. Homework? No, we don't have a homework for this session. This is just a workshop. So we just want you to gain knowledge from this and try to, you can probably try to set this up again and work on it. So could you please go through the boundary conditions? Okay, so boundary conditions. This is a question from Zohair Said. I'm not sure for which simulation you're referring to, so I would just take up one case and I would just quickly go through, or a case which has more boundary conditions in it. So, yeah, this one should be good. So in case we define a boundary condition for any topological entity, so we define it for any volume. In principle, you can even define it to volume sets. If you change this, it is possible for you to give it as the boundary condition of heat in any form. it can even be given on surfaces, assigned on surfaces with appropriate reference temperature, which is the ambient temperature in this case, and the heat transfer coefficient. Here, how we define this value of heat source, we calculate the volume of the whole solid, and then we want to define a 1000-watt load. So according to the volume and the power which we have to apply, so we just calculate the watt per meter cube load, and that is being defined. And so this is for convection, and in case of radiation, then as I told you, it is this reference temperature is again the ambient temperature, and the emissivity is going to be what I told you earlier with respect to the black body substance, or the emissivity with 1, which is a black body, and emissivity with 0, which actually does not accept or leave out any radiation in it. So I hope this answers. If you have any further questions, you can just post it on the forum. And could you please repeat and explain the slide of finite volume method? It's a question from Alexandro. Okay, Alexandro, here we go. Okay. Excellent. So finite volume, essentially all simulations are being calculated using subdomains. So we have the entire geometry divided into small domains called as, this process is called discretization. So in this case, they are small control volumes. And in case of finite volume method, all the values, say for example, which you would be calculating, and this is, since this is essentially being used for CFD problems, it would be, say, velocity, pressure, and so on. So all these values are being stored at the center of each cell. So basically the cell centroid, as you can see here. But in the other case, it would be at the nodes in the corner of the cells and not the center of the cell. So this is the basic difference between finite volume and finite element method. Okay, could you go through convection plus radiation? Okay, so I believe you're referring to this case with convection plus radiation. Oh, sorry. So in this case, you define the convection to some particular surfaces and also radiations to the same surfaces. So as you can see from the results, yes, so the radiation effects are being seen only after it reaches some high temperature. So within that range, convection is predominant, after which radiation comes into play. So you can see it from this image, the one in the bottom, where you can see you have convection plus radiation on the right, and you can see it never reaches the red domain on the top. But the image on the left actually reaches the red domain, because when you have convection and radiation, you have heat being dissipated due to both actions. So the temperature change is much higher than what you expect, as in what you see in the convection case. Okay, and okay, that's an interesting question. How much accurate the results are for real-world applications? And it's a question from Vivek Talapa. Thank you. And we actually have not simulated this. Probably we should have a research paper on this to take up and then compare the results. That would probably be kind of a validation case. So if you're interested, probably we can definitely do this, try to do this. And even if you would like to do this, then you can post it on the forum, and then we can definitely help you getting this out. Okay, and I see no more questions coming up. So thank you so much for attending this webinar, and we look forward for your attendance in the next 2 webinar sessions as well. So until then, see you. Goodbye. Have a nice day.